Banerjee.
Good evening, Mr. Prabhakar. Thank you for joining. So, good evening to all, and greetings to all who are watching this on YouTube. So, let's start today's class. The agenda for today's class would be first to finish the problem that was started in last class regarding the stiffness method to solve beams, and then I have received two suggestions from Mr. Prabhakar. First was regarding the current assignment of week 6. There was some confusion regarding the correctness of the multiple choice question answers. So the thing is, I went through that problem for the current assignment, and I was quite what to say. I was quite shocked to see that it was pretty similar to the present problem. So we'll solve today's problem. Let me open the today's problem. So today we are going to solve this problem in for frame structures, and it is it visible, the problem which we are solving today?
Yes, Mr. Ben. Yes,
Yes.
we can see that.
So it is pretty similar to what is there in the current assignment. However, there are some small differences, and so what I'll do is, when we'll solve the problem in class today, so you know what are the steps, and you can follow the steps exactly and find the answers. And if there is no matching answer, or if there is any incorrectness in the multiple choices, then I think you can contact NPTEL team, and they will give you sufficient credit related to that. So I don't think we need to discuss the same exact problem, but we can discuss the same exact procedure, and then regarding the correctness of the choices, that you can always take it up with the NPTEL team. So,
Sure.
and the second suggestion was discussion regarding the shear deflection of beams, if I am correct. So that what I have thought is, like, today we can finish these two problems for beam and frame, and that I can take up in the next class, because I don't think there is some, like, urgency to the discussion of that topic. So maybe we can finish everything today, and then we can take that topic up in the next class. Is that fine?
Yeah, that's fine. Because
Yeah.
why I raised that question is in the
Yes.
what are the tools we are using, Stat Pro. So that
Mm-hmm.
I think they've incorporated this deflection due to shear deformations in their analysis.
Okay.
So
Okay.
what happens if I analyze on cantilever beam that
Mm-hmm.
uh, uh, problem?
Mm-hmm.
I think at the free end also we get some moment or something. I don't know, some strange thing. But they said that that is due to deformation due to shear or something. They said that. So, but I searched that. But the topic is there, right? Deflection due to shear deformation. That concept is there in the
Yeah,
analysis.
concept is there. Concept we can discuss. Yeah, like how deformation takes place due to shear deformation. Yeah.
Yes. Okay,
Mm.
fine. We can discuss.
Okay. Yes. So let's start today's class. I don't think there is any need for my introduction. And last class, uh, we had covered till this point, where we had understood the how to calculate the loads for solving the P equals to KU, that is the stiffness method solution for the deflection and reactions in beams. So is that part clear? Last day we had a pretty long discussion on that, so that is now digested.
Yeah. I mean, I mean, different methodology to explain that thing. That's fine. I mean, we are clear on that. Yeah.
Yes. Okay. So today what we'll do is we'll just take what we had found in last class, and we'll solve the rest of the questions. So majority of the question was already solved in the last class, because the main part was like making the individual stiffness matrices, then assembling them, then finding the load vector, and then now what is left is, now we need to find what are the different displacements and what are the different loads. So I could see my p vector here, load vector. So let me write my load vector. um, or else let's go here. Yeah, okay. So this was my assembled stiffness matrix. Here we had already we already know what are the two displacements, two unknown displacements. The two unknown displacements are, number one is the rotation at joint C, number two is the rotation at joint B. So our first and second degrees of freedom are the unknown displacements and the known forces. So now what we need to do is, now our stiffness matrix, yes, like this. So our stiffness matrix is divided like this, where we know the P known and P unknown are the two parts of the load vector. The whole stiffness matrix is divided into four parts, and U unknown and U known are the two parts of the displacement vector. So from here we want to find u1 and u2, that is uu. So here uu equals to u1 and u2, that part is clear. And pk similarly would be p1 and p2. So we had already found the assembled stiffness matrix. This is the assembled stiffness matrix. So corresponding to degrees of freedom 1 and 2, 1 and 2, we have this as our stiffness matrix. This is the k known unknown. Okay. So now if we solve the problem, pk equals to kku uu. So here what is our load vector? P1, P2. Our stiffness matrix would be EI by 18, 24, 12, 12, 36. Please check whether these values are correct, consistent with your notes. These are even. Just one more thing. I think in the problem they have shown this as KK. So what I would do is I would write this as KK, not KU. Yes. Okay.
It is not having any physical meaning, right? Whether you call it as a KK,
Uh,
UU.
yes, yes, yes. It is all only matters in terms of like naming it. It does not have
Understanding
any
the
physical.
concept, okay. It
Hmm.
doesn't have any physical, because if
Yeah.
you change that displacement sequence, then accordingly even that
Yes,
will
yes.
also
Even
change.
that will change. Yes, yes.
Yes.
This is just a way of representing the
Okay.
partitioned
Agreed.
matrix.
Agreed.
I personally like the nomenclature as KU, and like this one to be KKU. The reason is that we have K first here and it is associated with U here. So these are some small tricks, not tricks, some small methods which we use in matrices. However, like it doesn't matter, anything can be the name. Yeah. So now this was our problem. So we already know P1 and P2. What was P1 and P2? Let's find out. So P1 was 3.75, P2 was minus 3.75. I am not iterating the procedure. It is available in the last lecture. So I'll just write down the answers from here. 3.75 minus 3.75 equals to EI by 18 24, 12, 12, 36, u1, u2. So this is simple solving of two simultaneous equations, or even you can just put the values and take the inverse of this matrix. So it is very simple. I am not asking you to solve this by yourself. I would just directly give you the answers. So the answer for this would be 1 by EI into 4.5 and minus 3.375. Okay, so these these are the answers for the unknown displacements. We have a new participant in this meeting, so can you please introduce yourself? Your name is showing as meeting guest. I'm not sure. Okay, maybe you don't want to introduce yourself, so we'll just carry on with the class. So as we were discussing, the unknown displacements are now solved from the stiffness method. These are the unknown displacements. Now what would be our next step after we find the unknown displacement?
It's unknown forces.
Yeah,
P3, P4.
the unknown forces, exactly. So basically the these will give us the reaction forces, right? So the unknown forces that we have, P3, P4. Okay, let's write it with the nomenclature itself. P unknown equals to K. What was the P unknown equals to this vector, right? K UK. K UK into UU. Okay, so now we have P unknown as P3, P4, P5, P6. We have K UK as EI by 18, 0, 6, minus 12, minus 12, 12, 9, 0, 3, and 1 by EI 4.5 minus 3.375. So this is E1 and U2 in the right hand side. These are the stiffness matrices PUK. Let's recheck. This is the stiffness matrix now, which we are talking about. This is KUK, and and so from there, this is the equation. So now it is pretty straightforward. You need to just matrix multiply this 4 cross 2 matrix into 2 cross 1 matrix. So you will get a 4 cross 1 vector, and the answer for this would be minus 1.125, minus 0.75, 1.3125, minus 0.5625. Okay, so this is the solution of the load vector. So now does these load represent the different reaction forces of the beam system?
Sorry, what is that question?
So do these different loads P3, P4, P5, P6, do they represent the different reactions at the supports?
No. We have to add those
No.
equations, whatever we found there.
Yeah, exactly. So we need to add these things. So we have considered P3 as R3, P4 as this equation, P5 as this equation, P6 as this equation. So from this we have 4 different equations to find R3, R4, R5, R6. We already know the values of P3, P4, P5, P6. So from here we can find the reaction forces as R3 would be minus 1.125 kilonewton meter. R4 would be 6 point, okay, let me explain the R4 further. R4 would be minus 0.75 plus 7.5 equals to 6.75 kilonewton. R5 would be R5 would be the same. No. R5 would be R5 had the fixed end moment, so R5 would not be the same. R5 would be 1.3125 plus 7.5. It is 8.8125 kilonewton, and R6 would be the same, minus 0.5625. Okay. So R3 and R6 did not have any other moments associated with moments or forces, so they are directly the loads P3 and P6. However, the others had the extra fixed end moments or forces, which we have already discussed quite extensively in the last class. So till this part it is clear what are how to find the different unknown displacements and unknown reaction forces.
Yep, yep.
Yes, okay. So well and good. So now this was the end of the questions that were there in that week's assignment, week 5's assignment. However, I wanted to add one more discussion on this, is like what are the member forces, right? Were you about to ask the same thing?
Yes, yes.
Yes.
So my question was, so we have to use that element matrix to find these member end forces, right?
Yes, yes.
But in okay, that's a method. But actually, we can take this force and we can manually calculate that with using that three equilibrium equations. We can find the moments, equations, and reactions, right? Because we know the
Uh,
reactions.
you know the reactions, yes, that is correct.
We can take
Mm,
that sigma m is equal to 0 to 1, and you'll get the moment at that
okay,
rate,
yeah,
right?
yeah, 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 yeah. You could also choose to use that method.
Method. I
Let me
mean,
just
this is okay
rethink.
for the methodology. Is I mean, okay, we have to use these
Yeah,
elements then
yeah,
as well.
yeah, yeah, exactly. Yes, like we already know all the reaction forces, we know the different distribution. Yeah, it's simple. Now you can directly find the bending
Yeah,
moment using
if we
the.
are writing some program, then it is understood. We can bring this stiffness matrix and we can find the member and forces. If we are
Yes,
doing manually, we can directly use the equations and we can find that.
exactly. Yes, yes, yes. From strength of materials class, yeah, or structure analysis one class also. Okay. So, however, like using the stiffness method, what we do is like we bring in the different force. Sorry, we take the local member level. Member level stiffness matrix, local stiffness matrix, and we find the different forces and moments in the beam. So, so this was our first beam element in last class. Do we remember? Let me show what was the first beam element. Yeah, for member one, this was the first beam element where we had the degrees of freedom as 6 3 5 2. So we have the stiffness matrix as 6 3 5 2 6 okay, 6 3 5 2 6 3 5 2. Okay, and then we now what we have is we already know what are the different displacements at the degrees of freedom 6 3 5 2. So we can use the deflection vector to find the different member forces. What we now do is say this is Q6 1 for member 1, right? Q3 1, Q5 1, Q2 1. Now we understand that for member 1 and member 2, the different internal moments and forces, that would be different, right?
Yes, yes, yes.
Yes. Okay. So EI by 18, and we have the individual stiffness matrix. The individual stiffness matrix, I will just copy it. You please confirm it with your previous notes. Okay. So now we already know U6. This is 6. What was the 6 3 5 2? So this is 6 3 5 2. Now what was U6? U6 in our case, U6. So 6 3 5 2, 6 3
Not
5,
6.
everything is 0. 2, we have this value, right? So 0 0 0 and minus 3.375 by EI. So is this fine?
Yes.
Yes. So now, is this all? This will give us the our required member stiffnesses, member forces.
Yes, we can get that member forces. Yes.
Yes. For this case, it is true. But if there is, say, a load also on the beam, if there are some loads, so we also have those fixed end moments, right? So we have to also incorporate those things. This is actually the okay. So let me use this color. So this will give you the forces and moments coming from the deformation. Okay. But
Okay.
we have to subtract the fixed end moment from this. So for the fixed end moment, in this case, it was all 0 for the first beam, right? So in this case, it is fine. You can just find the internal forces coming from the deformation. But in the other cases, it will not be fine, right?
Hmm.
is is this concept understood, that we have to also subtract the fixed end moments?
Subtract, or we have to add algebraically that FPMs. Which
Yeah,
way
we
to
have to,
use?
exactly. Yeah. So we have to actually add algebraically, but since the I did not want to say that, the reason is, like, we are always talking about forces and moments in this direction, right? uh, so we are always, whenever we are talking about these different degrees of freedom, we are associating the directions with that, right? So I did not want to mess up with the directions. Actually, for the fixed end moments, the directions now could be different. Okay. But since we have already discussed about the fixed end moments here, you remember, right? Here we have discussed about the different fixed end moments and for the given directions. So I
Okay.
wanted to, like, use the same fixed end moments and say that we have to subtract the subtract the fixed end moments, right? So just to not confuse more with the different directions, I want to keep the directions consistent and then use the different deformation and fixed rate moment. But basically, you are right. It is actually add algebraically, not subtract. So very good. Thank you for pointing out that. So with this, we can find the answer for this one. The answer that I have got is this. You can also please cross check with your own calculations. This answer was not there, like this question was not there in the assignment, so I couldn't cross check with their the assignment calculations, but still I am pretty confident these are the correct answers. The reason is, like, if we now find the different member forces for member 2, then we could easily relate that at the same joint, like at the joint B where the two members meet, the forces should have some equilibrium, right?
Yes.
So from there you can understand whether your answers are correct or not. So for member 2, I would again draw the member, and we would again find the member forces. Q5 2 this time, Q2 2, Q4 2, Q1 2 equals to EI by 18. This was 8, 12 minus 8, 12. This was 12, 24 minus 12, 12. This was minus 8, minus 12, 8 minus 12, 12, 12 minus 12, 24. Are these correct? I hope these are correct. What are the different degrees of freedom associated with it? We have 5, 2, 4, 1. I forgot to write 1 here. Okay. So now 5, 2, 4, 1. So 5 was 0, 2 was minus 3.375 by EI, 4 was 0, 1 was 4.5 by EI. Okay. So, and again subtract or algebraically add the different fixed end moments. The fixed end moments would be like this: 7.5 minus 7.5 plus 3.75. Okay. So okay. uh, just one more point that I wanted to add in this context is, now we are also saying that we can just subtract the fixed end moments or algebraically add, right? So basically what we mean here is that if these are the fixed end moments, then we subtract. If we are taking the equivalent loads on the joints, then we add, right? So we have the equivalent load on the joint that is in the opposite direction, and I'm sorry, did I say just the opposite?
Yes.
Yes. So okay, so if we are taking the equivalent loads on the joints, then we just subtract, and if we are taking the fixed end moments which are in the opposite direction, then we add them, right? So that was the point. Okay. So now after solving this, you will get the answer. Which answer? Okay. After solving this, you will get the answer 8.25, 2.25, 6.750. Okay. So this is 5241. This one is 6352. Okay. So now what we can see is
5 is not matching.
5 is not matching, correct. We can see that. We can see 2 is matching, right? Equal and opposite. Okay, 2 is matching. We agree on that?
Yes.
5 should not match. Why should not 5 match? Because we have a reaction force in 5. Where we have a reaction force on 5. Okay, so the
5 is the reaction. 5 is reaction.
yes, 5 is the reaction force, like 5 is the upward direction force.
Okay, okay.
Yeah, so just in the left hand side of the beam we have some force, shear force,
Agreed, agreed.
then the reaction,
We
then
need to add
alpha.
both the things to get that reaction, basically.
Exactly, and if you add you will get, this is how much is this? This is 8.25 plus 0.5625, you can get 8.8125. Where is that?
Yeah.
8.8125, this one.
It is, we can add a shear force diagram. If you add that, you'll get a reactions, basically.
Exactly, exactly. So this is matching. Then in the right hand side, one side it is 6.75. 6.75 means the reaction, vertical reaction. And what should be the moment at the end? It should be 0, right? So I think our answers are correct. So this was all regarding the beam problem, and we have just finished in the correct amount of pages. Go to properties of eigenvalue. So I would just write a note here, somewhere here. Let's write somewhere here. This. Okay. So with this, we can close this chapter, I guess. Is this fine?
Yep, yep, yes, yes.
Okay. Okay. If there are no other questions, then we move on to week 6 problems. Okay. So basically in today's class you are the only attendant, so then you will have to give me all the answers for the week 6 problems. Yeah. Okay, so let's start with week 6 problems. First of all, like in week 6, what was our course? Our course was um, solving frame problems using stiffness method, right? So before we start solving the problems, let us revise our concepts that we have learnt in the course. First of all is, this is one beam, say, not a beam, this is a frame element, okay? So what is the difference between a beam element and a frame element?
Just we need to take care of the axial
Exactly,
stiffnesses.
yes. So we need to just take the extra axial reaction. Okay, 4, 5, 6. This is a frame element, and now I'm going to write the element stiffness matrix of the frame element. So the derivation for this is pretty simple. Uh, just the juxtaposition of the two stiffness matrices of the truss element and the beam element, right? Okay. So what are the different element matrix values? First one would be AE by L, right? 0, 0, 0, 0. First one, if we just see the 1 and 4 degrees of freedom,
No, force should be minus. AE by L.
Oh, sorry. Yes. Thank you. Hmm. If we just see the first and fourth degrees of freedom, this is just like one truss problem, right? So when we have a truss problem, what is our stiffness matrix? AE by L minus AE by L, then minus AE by L, AE by L, right? So first and fourth, let's write that. So now our stiffness matrix for the element frame element only represents a truss element. Now if we have to add the beam element, what we have to do? We have to do all the others truss element degrees of freedom as 0, right? And then we have to write the beam stiffness matrix in the leftover parts, right? This is pretty simple, like you don't need to remember anything specially, you just need to superimpose both the truss and beam elements. Okay. Please correct me if I'm doing anything wrong in between. Iron square. So this is the stiffness matrix of one element of frame, right? Pretty
What is the
straightforward.
unit of that 6E by L square? Is it a kip or kip per inch? Can you just check the units?
6 EI by L square. Okay. Hmm. So what is happening basically here is you are telling this because there are different under EI there is different degrees of L, right? So the units must be changing, right? That.
Because if you consider that degree of freedom 2, two
Mm-hmm.
second column and the third row, it is a moment, right?
Okay. Degree of freedom 2. 2 is a force. Degree of freedom 2 is a force.
And
And
row number 3 is that's the moment
row
generated
number
due
3
to
is
that
a yes, row number
moment.
3 is a moment. Yes.
So what will be that unit? 6 EI by L square. Because similarly, the degree of freedom, you are whatever the moment you are applying at 3 degree of freedom, row
Hmm.
number 2, that is a reaction what you are going to get.
Hmm. Hmm.
3 2
Okay.
is a reaction, 2 3 is a
Yes.
moment.
Yes. Let me just write.
Hope I'm not confusing
One.
because
No, you are not confusing. You have raised a very nice question. So, 1 degree of freedom 1 is a force, the axial force.
that is clear. Keep per
Okay.
whatever that
4
kilonewton per
is axial
millimeter,
force.
whatever is that.
Okay. 2 degree of freedom 2 is a reaction force, vertical reaction force.
Mm-hmm. Mm-hmm.
5 is a vertical reaction force. Okay. 3 is a moment. 6 is a moment. 3 is the moment, 6 is the moment. This part is clear.
That is clear. Yep.
Now, having said that, let's see. Degree of freedom 1 is a displacement, is the axial displacement. Degree of freedom 4 is the axial displacement. Degree of freedom 2 is the vertical displacement. Degree of freedom 5 is again the vertical displacement. Degree of freedom 3 is the rotation. Degree of freedom 6 is the rotation. Okay. So now when we have the units of displacement, it is meter. Meter. This is actually uh,
Radians per
radians. So
kilonewton per
means
radian. Okay,
unitless.
you're applying the rotation itself. Okay, radians. Okay, clear.
Yeah. Radians means basically unitless, right? So now when we multiply this with, now I think it is clear, right? Do I need to explain? Okay. Just for the sake of completeness, I will just explain one more step. That would be
Because
for.
of row number, I mean, column 2 is a displacement. Okay.
Hmm.
Because of that, in the degree of freedom 3, we have to get a moment. 3.
Okay. Just give me 1 minute.
Yeah, yeah.
I will just. Yeah. So now all the forces are say in newtons, and all the moments are in Newton meter. Okay. Hmm. Now what we were saying, please can you repeat your question? Row number and column number.
Column number 2. Okay, that
Column
is
number 2.
2
Okay,
degree of
this one.
freedom.
Yeah.
And the 6 EI, that is that row number 3. That is that 6 EI by L square.
Row number 3. Okay. So now when we are talking about column, what do we know? We know if we are talking about column, it is associated with the degree of with the displacement degree of freedom with u, right?
Correct, correct.
So if we are talking about column, this one is the vertical displacement at point A. Say if we name this at point A and B. Okay.
Correct,
So
correct.
so vertical displacement at point A is represented by the whole column 2. And now we are talking about the element at row number 3. So row number
Yes,
3.
4 generated at degree of freedom 3 because of that vertical displacement.
Exactly.
3. Yes.
Exactly. Yes. So now in row number 3 we have the moment. We have the moment at force
Exactly.
A. So
Correct.
and just if we compare, at row number 2 we have the vertical reaction at point A. So vertical reaction at
Exactly.
point A due to the vertical displacement at point A itself.
Clear,
Okay,
clear,
so this is the
clear.
diagonal element. So in
Correct.
that case, we are getting a force in Newton with a L cube divided to that 12 VI. Okay.
Agreed.
So
Agreed.
now if we need a rotation in Newton meter, we need to reduce the degree of the length in the division. If we are wanting one more meter in the top, we have to reduce it from L cube to L square. This is, I am just talking in terms of the units, and obviously you can derive, and we have already derived this in class.
Mhm.
Okay. So did you understand my point of view in terms of the units? So if we are say for this element, we need Newton. For this
Correct.
element we need Newton meter. but
Exactly.
but whole this second element is actually meter,
Okay.
right? Because this is the vertical displacement at point 2. So vertical displacement at point 2 is always in meter. So but in row 2, if for the force we need in meter, and for the rotation we need in Newton meter. Okay.
Correct.
So we need one more meter at the top.
Exactly.
So we reduce a meter in the denominator.
No, I mean,
Uh-huh.
see, if you put a units for EI and L square,
Okay, yeah,
we are going to
yeah.
get Newton only, not Newton meter.
Okay, just in that context, let's just make one thing clear. EI by L cube into L will give us Newton.
EI
EI
by
by
L
L
cube.
cube into L will give us Newton.
Okay. EI by no EI by L cube directly gives the Newton, not into L.
No, no. This is the stiffness.
No, I'm just getting confused.
EI by L cube will give us the
E is
stiffness.
E is a meter for no, sorry, meter per Newton per meter square. E
E is
value.
Newton per meter square. Okay.
I is a meter to the 4,
I is meter to the power 4.
and L cube meter cube.
L cube meter cube.
Okay, if you multiply it by another meter, you will get in Newton. Otherwise, it will
Yes.
be Newton per meter.
Yes.
Okay. Okay. What I got confused was EI by L cube. It gives Newton per meter. What I that if you apply that force, you will get. I mean, that is the stiffness per meter. Force. That is
Uh,
what I mean. Newton
yeah,
per meter.
stiffness is like force per unit length. So always force per unit
Okay.
length Newton per meter. Stiffness
So
is
12 EI
always
by cube is the only Newton. It is not a Newton per millimeter. That is a force generated due to unit displacement. 12 EI
yes,
by L cube is the force generated due to unit
unit
displacement.
displacement. Yeah, then you have to
Okay.
multiply the displacement with that.
Okay.
Okay. So
So
EI by
6
L
EI
cube
by
into
L
L
square.
will give you Newton. That part is sure. Yeah, yeah. Please go ahead.
So EI by L square gives what? Only Newton. Again.
Yes,
No.
exactly. So EI by L square, what will EI by L square give? So basically now we are talking about EI by L square.
Is Newton. Just Newton it is.
It will be just Newton, yeah. And why is this L square required? Just what to say? So just let's forget about this EI by L square. So we know
Mm-hmm.
this EI by L to the power something, say n, okay,
Mm-hmm.
into L. We require. Oh, let me just. Let me write it over here. So we know EI by L cube into L will give us Newton. That's fine. So now when we are talking about the third row and second column, we want EI by say L to the power n. We don't know n, something n. Into, we already know second column. So we are already multiplying with L. Okay.
Mm-hmm.
Should give us Newton meter.
Exactly.
Yes. So now you will find that n should be 2. N has to be 2.
Agreed. But I didn't understand the logic because my thinking was that
Yes.
6 EI by L square should give me the unit in Newton meter. That was my understanding.
6
So
EI by
because that is a
L
moment.
square. Hmm. That is the moment per unit length.
Unit length of
That is the moment generated. So, okay. Let me. Hmm. So, this is the beam A and B. Now we have been very specific, right? We have been very specific. We are only talking about the
2 and
um,
3. Yes.
2, okay, only this displacement, okay. So
Okay.
if we find this displacement, then how will our beam react? Say something like this.
Correct.
If we give a unit displacement on the beam, okay.
Yes.
So now with this we have all these red are in forces and moments, okay, but our displacement is fixed. So now this is 1 2 3 4 5 6. Now we are getting more specific. What is what is 3? Okay, so 3 represents the moment. 3 represents the moment, that is clear. Moment at joint A, that
Mhm.
is also clear. Due to what?
Unit displacement, vertical unit
Due to
displacement.
unit displacement
Unit vertical displacement. Okay,
at
whatever.
2. Okay,
Mhm. Mhm.
so what should be our units for 3? The units for 3 should be moment at joint A
Exactly.
due
Mhm.
to unit displacement at joint 2.
Okay. Mhm.
This means Newton.
Okay. Mhm.
Newton meter per meter.
Mhm.
So that's
Got
how
it.
6 EI by L square.
Okay, if you take that, okay, this is clear. Okay, this
Okay.
this gives the Newton meter per meter
Meter.
displacement. So you'll get a
Yes.
Newton
Yes.
thing. That's okay.
Hmm.
But if you take the same third column, second row,
Okay. Let's take third column and second
second
row.
row.
Okay.
Okay.
Hmm.
So that is the third is the you are providing a unit rotation
Okay.
at 3,
Yes.
for which we are getting a reaction in
Yes.
direction 2.
Yes.
So that is again should be a, what is that unit? It should be a Newton.
Yes.
Correct. So we need not to multiply again anything with meter or anything. No.
So here comes the, like, you have already answered your question through your question, but like you did not hear your own self while you are talking. So you told that this is this one, the third column and second row. You told this is the force at direction 2 due to the unit
Unit
rotation
rotation.
at 3. So what we
Okay.
have the units as rotation? Rotation is radians.
Okay.
So unitless.
Mm-hmm.
Okay. So now 6 EI by L square, we know EI by L square is already Newton.
Okay. Okay.
Okay. So EI by L square
Okay.
is already Newton, and that is due to the unit rotation. So Newton
So it's
divided
a
by
rotation, no,
radian.
no units. Okay.
Rotation
Got
has
it.
no units. Newton
Okay.
divided by
That's a,
radian, which gives us Newton again.
okay. Clear.
Clear?
I mean, it takes a lot of time to go
No,
into.
no. It's fine. It's fine. Like, I am happy that you are coming up with these queries, because people generally just take whatever is spoken in class and not think over it. So these are very important questions. Like, when you actually think of these things, like, why are there different levels of L? There is one single L, then there is L square, then there is L cube. So why are they there, and then what is their significance? So these will reduce all chances of any doing any mistake, because the stiffness matrix is very very informative in itself. So if you are just doing some, like, if you have memorized the stiffness matrix and you just replace one L square with L cube, your units will not match. Then you will find out, okay, so there must be something wrong there. And because L is quite a large number, right? So maybe 5 meters, 6 meters, so your answers will also be drastically varying. So these
Exactly.
will, yeah, so these will give you a very good indication on where you are going. Are you writing down the correct stiffness matrix or not? Like, even without memorizing, you can just
Yeah,
think
definitely.
and write the stiffness matrix.
Because I got confused because I mean, always I was thinking unit rotation Newton meter one. So you said that we are providing a unit rotation, not we are not applying a moment there. We are applying a rotation. We are not
Yes.
applying the moment there. Okay.
Yes. Yes.
Okay. Thanks, Mr. Banerjee.
Yes,
Thanks.
yes,
Thanks.
no, no problem. Yeah. So, So this part
Probably
is
for
clear.
others it will be easy. For me, it is quite difficult. So I just dragged into this discussion. So that's it.
No, I am not sure whether it is easy for others also. Like, yeah, like you need to give it a good thought. Like, I am not sure how many people give it a good thought, because stiffness matrix is very straightforward in itself, right? You just write the correct stiffness matrix. You just put the values. That is why it is famous for computers. That is why it is used in computers, because you don't have to think it through, right? So you just give
Computer
the,
never thinks the unit. Computer
yeah.
never thinks the unit.
Yeah, computer will never think the units. So it is easy to also get away with understanding less in stiffness matrix, but the beauty of the stiffness matrix is it is very very informative. Like, I even
Sure.
remember, just diverting from the class a little bit, in my undergraduate college, I went to give the grand viva. So grand viva is a kind of like viva after the third year of college. So then they will ask you questions from any part of the undergraduate course, and they just asked me one question in the grand viva on structural engineering, and they just told me you write the stiffness matrix for a frame element, and that's all. And so if you could write it correctly, then they would know that, okay, like, you have understood that which degree of freedom correlates to which thing. So it's very important, actually. Anyways, getting back to our discussion. So this was the element stiffness matrix for the frame element, and we have already derived it in earlier classes, and also this was done quite extensively in the this week's lecture videos. So now now what we basically did in the element stiffness matrix of the frame element is we merged two elements, one truss element and one beam element, and we just put them together. But if we remember, when we did the problem for the truss element, we had some transformation because the trusses were at different angles. But for the beam element, we did not have so, because beam was always in the horizontal plane. It is always like having the same angle. There is no beam like going like this, like any triangle. Okay. So what will happen if a beam goes like a triangle, like this? Like, we have only studied beams to be straight, right? Like this, say A, B,
Yes.
C. What will happen if beams will go like this, a triangle, say?
It becomes frame.
It becomes frame. Yeah, yeah, pretty simple. That was what I am going to say. So
Okay. I mean,
yeah.
what happens if it is only a single beam at, at inclination with vertical load, not a load perpendicular
Yes.
to the beam?
Mm-hmm.
You have an inclined member.
Yes. So it will
Okay.
become frame. It will become frame. The reason why it will become frame is there would be, like, whenever there is some good vertical angle or something, so then the load will always induce some compression in the member. If you give some vertical load, right? So you cannot easily neglect the axial deformation in that
So we have
beam
to treat that as a
as a frame element.
frame
Yes.
element with the 6 by 6 matrix, and we have to do that.
Yes. 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 So basically
Or
that.
directly we can I mean, resolve that forces in two directions, and we can algebraic, I mean, we can take that ratios, compression stress and the bending stress in that. We can always resolve that vertical force into perpendicular to them and in the longitudinal directions, right?
Yes, yes, and basically, like,
I mean, we can
if you are breaking down that into two and then solving, what you will be basically doing is you will be solving one beam problem and one truss problem.
one beam. That's it. Different.
Yes, so you can just directly solve it with the frame problem. Yeah. So even in the lectures also, I think, like, even professor only talked about like how you just merge the beam problem and the frame problem to get the beam problem and the truss problem to get the frame problem, because that is only the part of frame. Like, there is nothing more into it. Anyways, so but the interesting part is, like, but now since this will have some axial deformation and this is taken from the truss problem, we will need one transformation matrix. Okay. So it is not so simple as the beam. So, and the course of like matrix method in structure analysis, this course is also developed very beautifully, I think, because first we discuss about the trust problem. It only has 2 degrees of freedom in the local direction. Okay, so now you take a very simple thing, then use the concept of transformation matrix to change the angle of trusses. So this gives you some idea on how to use the transformation matrix, but on a very simple problem with 2 degrees of freedom. Then you come to the beam problem. In beam problem, you forget about the transformation matrix. You just have a single beam element in horizontally inclined, and then you, what do? You include the different fixed end moments and then transverse loadings on the beams, and you find a good insight on how your beam reacts, on how your what happens in actually loaded members like truss elements. It only compresses, it only has tension or compression, elongation or compression. Okay, but for beam elements it is little bit difficult to visualize that how it is bending and what is happening and why we are needing 2 rotations and then deflections and what is happening over there. So uh, so then you understand those parts of the things, and then in frame problem you already have the basic knowledge of the transformation matrix, and you already have the basic knowledge of the deformation due to transverse loads. So now you can just merge them together and you can quickly solve the problem. Just summarizing the whole idea once, and I think this is very interesting and this is very beautifully designed. So moving on. So now for the transformation matrix, what should be the transformation matrix for a frame problem? So the interesting part is, if you take this element, okay, let me draw something over here. So if you have an element like this, if you convert it to an element like this with some angle, say theta, your forces and displacement, your forces will change. The different forces that was there will change. You will get some new forces and new reaction, new forces, right? But what will remain same is the moments. The moment was already, say, anti-clockwise, it will still remain anti-clockwise. Moments will not undergo any change, right?
Agreed. Agreed.
Yes. So that is why you can very easily, what you can do is you can write, okay, let me just write. This is 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So what you can basically do is you can write at 3 comma 3 it would be 1, at 6 at 3 6 comma 6 it would be 1, and that's all. Like why 3 comma 3 and 6 comma 6? So and also in all the other elements in these row it will be 0. Yeah, so this is basically representing that the moments that you will encounter, this will have the same meaning in the transferred axis as well. And over that we also know that there is no relation between the moments and the different transformation of the forces, like the moments and forces are independent to each other. So we can write this down. After writing this down, the rest part is pretty simple. The derivation of this, I think, is it done in class? Even if it is not done in class, this is very simple. I don't think there should be any problem with this derivation. Um, so the answer is lambda. Yeah, I think it is done in class, right?
Yes. Yes. Yes.
Yes. So my job was to like discuss the problem solving part, so I did not go into the derivation, but it is very simple also, so there should not be any worry. So the derivation is fine, right, for this?
Yes, yes, no
Yeah,
issues. Yep.
yes. Okay. So this is the transformation matrix. So now we have the transformation matrix, and we should always remember the definition of theta. I have discussed this in detail when we discussed the transformation matrix for truss elements. Like, this theta is very important. This is the anti-clockwise rotation from the first point, like from the first joint of the local element. Okay, this is theta. So with this, you know the transformation matrix, you know the element stiffness matrix. Now you just need to transform. Like, how do you use the transformation matrix? You use the transformation matrix as dx1 dy1 dash d1z dash. Why am I using dash? I think this is the mm, same nomenclature that is used in the class, maybe. Okay. So basically, I will not write everything down. I don't think that is required. So basically, d1 dash equals to d1. Okay. So here, capital D is the global degrees of freedom, and small d is the local degrees of freedom. And now similarly, we know that f1 equals to t transpose f1 dash. So again, here capital F is global and this is local. So now what we already know is, we know F oh, sorry, this will not be d1. So let's just write small d and not forget about all these things. These are all understandable. Okay. So now we already know that F equals to K. What did we write? Ke, we wrote Ke into D. Okay. If we put the value of D and value of F, we can get F equals to T transpose Ke into T into D. I think this is pretty much known, so not much discussion required. This is the global stiffness matrix, and this is very important. And we don't multiply these things and remember the global stiffness matrix. We do this for individual case to case basis. Okay. So the global stiffness matrix is understood, right? I think it is understood. So
Sorry, I missed that question, Mr.
yeah,
Banerjee. What is that?
yeah. So the global stiffness matrix is understood how it is
Yeah,
derived.
yeah, it's
Yeah,
clear. Yeah, it's
yeah,
clear.
it's clear. Okay. So now moving on to the current problem in hand. So this was the problem in hand, and I was quite astonished to see that it is pretty much same. I'm sorry. So it was pretty much same as the problem for this week's assignment. However, there are some small differences which I should not like point out. You could see for yourself. So let's start with the problem. uh, I think the problem size has been a little bit smaller, but anyways, this is visible, right? The problem. Yeah. I think this is visible, right?
We have to make slightly zoom. I can't read the numbers, Mr. Banerjee.
Okay,
What is that?
okay, okay, okay.
A,
So
B,
what
C. Okay, I can read A, B, C.
what I can do is, maybe I can draw it in a big scale. So this is 6 unit. This is 6 unit. That's all. There are loads like this, which is 100 unit, and the different degrees of freedom are given as 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, now it is clear. uh, One very quick, what to say, like, the problem has been made very easy. Can you say why is it so? So means, like, what I'm trying to say is that in my opinion this is a very easy frame problem. Why is it very easy?
Because for one member, I don't think we need to take up any transformation matrix for
Okay, yeah,
horizontal beam. We can
yeah,
directly take that
yeah.
because that element matrix and global, it will be same if I am right.
Yes, yes. So yeah, you are correct. One member, there is no requirement of transformation matrix. It will just be one identity matrix. In the other member also, the transformation matrix is very simple. But the most easiest part is like those parts which you have taken time to think over and understand regarding the fixed end moments and those things. There are
It won't be there.
there is no transverse loading on the beams and on the frame, like on the frame elements basically. So you don't need to bother about the different were fixed end moments and those things. So one student who might be not very well equipped with those concepts can easily get away in this kind of problem, because there is everything is zero. So whatever he thinks about the fixed end moments or the forces and everything, he just needs to find the correct answer. So that's why I feel that this problem is very easy. We can quickly solve this thing. And so the given data for this problem is AE AE equals to 6 unit and EI equals to 18 unit. Okay, so yeah, so now the first question, as always, what is the degree of static indeterminacy? And what is the
Can you write the node nomenclature ABC, which is ABC? It is
yeah,
written.
I will just write, this is A, this is B, this is C. Okay. So this is the degree of, what is the degree of static indeterminacy for this frame structure?
These three
Yeah, it is 3. Perfect. Degree of kinematic indeterminacy?
is three.
Also 3. Yeah, perfect. Perfect going. So, uh, did you like have you planned to take the exam for this course?
Ye- Yes, I don't know how I'll do that,
Okay.
but
I
anyway,
think you'll do well. You have at least learned those things, how to find the degree of static indeterminacy and kinematic indeterminacy. So so
after these many years sitting 3 hours and writing, man, that is a problem.
uh, how
Solving, I mean, working with calculators. I mean, it's
mm-hmm.
quite
That
difficult
is
because we will not have that speed. We will not have a speed. That is a
mm-hmm.
problem.
But I feel you'll do good. You don't worry
But
about
anyway,
it.
I'm not bothered
Mm.
with the certificate. I wanted to just, I
Yeah,
mean, refresh my thing. That's it. I mean,
yeah. No problem. uh, I just hope that attending these classes for 2 hours a week helps. Yeah. So yeah. So now we have the two members, as this is as member one. Okay, we have used this code. So this is member one. This is member two. Okay. So now I will just ask the answers from you. So say this is member one we are talking about member 1 now. We have the different. Here, the degrees of freedom are taken sequentially, and not as like where there is the degree of kinematic indeterminacy. If we
Okay,
have
to do
to
the
take,
partition later. Probably you're
yeah,
going to do
yeah,
the
yeah,
partition
we have to rearrange the stiffness matrix
rearrange to
later.
get the
Yeah,
partition. Yes, yes.
yeah, that is correct. But there is also one advantage of this kind of degrees of freedom. Can you say before we get to that point, what could be the advantage?
Uh,
I'll just, there is one very nice advantage of this. Yeah,
we can
just
write it in ascending order that matrix, that degree of freedom, while we are writing the numbers
uh,
1, 2, 3, 4, 5,
yes,
6,
yes,
and
yes, yes, kind of that. Like the advantage is that everything, yeah, everything is in say order, so you don't need to bother about like what is the degrees of freedom number, and more importantly, since this is a frame member, right? So you have 3 degrees of freedom in common, and you all are in sequence. So when you are assembling the global stiffness matrix, you just write your first stiffness matrix here, and then you write your second stiffness matrix here. Okay, and then you put everything else 0 0 0 0. I am
okay,
not
got it.
bothering about this thing. So
Assembling the global stiffness matrix. Yes,
assembling the global stiffness matrix becomes very very
agreed,
easy.
agreed.
Yes,
Okay,
yes,
I can write the top diagonal that side. This side will write the rest. I can write it as 0 0.
yes,
Yes.
yes, yes, yes. Assembling becomes very simple in this case. So, so then,
Okay. I forgot to drop
yes,
a question. Okay.
yes, yes. Please go
What
ahead.
is the advantage of this banded matrix other than the storage space in the computer? Is there any, I mean, meaning or to know anything particular about the banded matrix?
Okay, about the
Why it is so
banded.
important about the banded matrix? I mean, I quite often read or heard about, okay, you'll get a banded matrix, banded matrix. I mean, what
Hmm.
it is exactly?
Hmm. Okay, let me think about it. One thing is the storage part that is, I think, mentioned in the lectures, but I am not sure about what could be the other advantages of the banded matrices.
Otherwise, I'm not seeing anything major to knowing that. I mean, we should have a band. I mean, if you, as long as you're maintaining the degree of freedom and numbering, so it doesn't matter whether you get a banded matrix or. I mean,
Okay, okay. Now, so there is one more factor to banded matrices, which I am not sure whether that is correct in this context or not. But maybe when we talk, we kind of think about those factors. So one factor is like building matrices. When we are talking about buildings, say this banded, I am not talking very specifically about any kind of benefit of this banded matrix as such. What I am saying is that if you find that your matrix is not banded, then you could understand that there might be some problems. Okay, so there are some serious physical implications of this banded matrix. So I am talking about that part, but not as such like is there any benefit that it has to be banded, it cannot be not banded, not like that. So so say you have a multi-storied building structure. Okay, say m1 m2 m3. So basically what this m1 m2 m3 represents is your masses that are lumped at the 3 story levels. Why are the masses lumped at the story levels? Because there you have the maximum mass, like the slabs and beams and everything. Okay, so then you have different stiffnesses of the columns, say k1, k2, k3. So now what happens is this is basically, say you are representing as this kind of system, a 3 degree of freedom system with 1 2 3 masses, and the stiffness is like this. So basically what do you mean is, this is a kind of, this is a kind of uh, stiffness arranged in series. Okay, so if there is something arranged in series like this, so why do you get a banded matrix in this case, is that your two members are arranged in series. Okay, so your two members are arranged in series like this. Okay, so that is the reason you get a very nice banded matrix. Okay, so when something is arranged in series like this, when you have three stiffnesses like this arranged in series, so what basically happens is, you could see your matrix becomes banded. So okay, I will just write the exact matrix values. I do not expect you to know these values right now, but I can guarantee you these are correct. Okay, so I have only taken 3 degrees of freedom, so this is a very small matrix. So this is a 3 cross 3 matrix. Okay, that's fine. So now you see that this is banded. This is banded. I have not taken a bigger matrix. A bigger matrix would show the effect of being banded very more profoundly. But say if we still we can find that this 3 cross 3 matrix is also banded. So this has a very important physical significance. What does this mean is, now everything comes to the stiffness matrix, right? So the degrees of freedom associated with these are 1 2 3 1 2 3 like this. So the element at 3 1 and 1 3 are 0. So what does that signify? This signifies that there is no effect of any change in 1 to 3, and there is no effect of any change of 3 to 1. So how do you understand that? You understand that there is no connect between 1 and 3. Okay, so if 1 and 3 are not anyway interacting with each other, these interacting degrees of freedom always are 0. So similarly, if you say I have taken a small matrix, let me take a big matrix. Let me just without drawing, let me just write it for a 4 cross 4 matrix. Okay, k1 plus k2 minus k2 0 0. Okay, but I think I will have to draw, otherwise I cannot make my point. Mm. Okay. Okay. So any system, say, of this kind, okay, say k1 k2 k3 k4, here I am drawing it as a spring, but it can be anything like a beam element, a frame element, a truss element, anything. Spring is basically a truss element. Okay, it only has elongation and compression. So these banded nature of the matrix, what does it signify is, there is no interaction between K1 and K4. So all the interacting elements between K1 and K4 are 0. Similarly, there is no interaction between K1 and K3. So all these interacting, okay, let me write 1, 2, 3, 4, 3, 4. Okay. But for K3, you see there is always interacting elements with K2 and K4. So there is some connection between K2 and K4, but K3 is only free from K1. So I don't know whether I can make my point, but do you understand anything from this?
Somewhat it's fine. Okay. I think
Mm.
it is a vast subject. Something goes top of my head. Okay. I think
Yeah,
we
yeah,
can
yeah.
go back to our assignment. I mean,
Yeah, yeah,
frame
yeah.
problem. I think.
Yeah, we can go back. Yes, yes. Just, just I will give it one more try. So if we take the joints, okay. So these are the
What you're
different.
telling is K3 stiffness will not have any impact on the analysis with the changing in the K1. Is that what you're telling?
Yes, yes. I'll just give it one more. I'll just explain one more thing here. Say you have these are the black dots are the different joints. Okay. So say you have deflection U4, U3, U2, U1, and this is ground. Okay. This is
Mm-hmm.
fine. So now, where if we are talking about U1, any displacement in U1 leaving everything else out, okay,
Mm-hmm.
will that have any effect on K3 or K4? Just think about it. If you just displace U1 like this, if you just hold U1, if you just hold U1 and displace
Agreed.
it like
Agreed.
this,
Got your point.
so
Got your
it
point.
will have
So
only
there won't be
effect
any
on
change.
K1 and K2.
Agreed.
Yes.
But
So
why K2? Okay, if you.
K2 also na this U1 this U1 is holding K1 and K2 in place. So if you move to the left, K1 will elongate, K1 will shorten and K2 will elongate. You move to the right, K2 will compress and K1 will elongate. So if you just
Okay.
hold it and move it,
K3 K3 spring will not compress because if you are moving U1.
yes, yes. Everything rest is say kept in zero. Like if you are holding all the four things, say U1,
Mm-hmm.
U2, U3, U4, you are holding everything. You are just
Mm-hmm.
moving U1 and U2. You are just moving U1. Okay.
Mm-hmm.
You are holding everything else. You are just moving U1. Okay. So you will only feel resistance from K1 and K2. K3 and K4 will not participate there. Do you agree?
Okay. Yeah. Yeah.
Yes,
Clear.
yes.
Mm-hmm.
So now for now again, like from basic truss problem to beam problem to every problem what we are discussing is the column the column represents the displacement and the rod represents the resistance. The resistance means the stiffness multiplied the displacement means the force. Okay. By resistance I mean the participation of the stiffness. So now we were moving the one element U1, right? So you see
Mm-hmm.
element 3 and element 4 of the first column it is 0 because this third stiffness, because K3 and K4 are not participating in the forces due to the first displacement U1. Can we understand?
Yeah. Yeah. Clear. But
Yes.
my question is U4.
Yes,
Okay.
U4.
If you move that U4, definitely K1, K2, K3, K4 all will have some
Huh. No, no,
interaction with
yeah,
that
yeah, yeah.
displacement of the U4, right?
So what I'm talking right now is like you are holding all the force. Like we have two of us are here in the meeting together. We have two hands each. We hold we hold all the four together, and then only one of us move only one hand, and the other one is kept intact. We are not moving any other. So this is
That's okay.
Yeah.
That is applicable for U1. That I can understand that. If you
Okay.
are moving a U4,
Yes.
okay, if you are
Yes.
moving U4,
Yes.
giving some small displacement for U4,
Yes.
definitely K1, K2, K3, K4 will have some
Hmm.
impact, right?
Again,
For
I'm saying,
U4.
like, we are holding U1, U2, U3 intact at our places.
Okay, got it.
We are
Okay, so
moving
that is not
K4.
moving. Okay, that you are locking and only you are moving U4.
Yes,
Okay,
yes, yes, yes.
okay,
So, so basically, what this banded nature suggests is that your members are in series to each other. Okay. So if your members were in parallel to each other, say if there is something like this is K1, this is K4, okay, and this is K3. Ah, this is K1, this is K4, this is K3, okay. You only have U1 and U2 say here, but here you cannot make that kind of banded nature because you K4 and K1 all are like contributing to your stiffness.
agreed,
Okay.
agreed.
So this banded nature, I did not answer your question at all that what is the benefit of this banded nature, but what instead discussed about is that why we want this
Why
banded
we get
nature.
band matrix? Why we get band matrix?
Yes, why we get the banded matrix? This is due
Yes,
to the series combination, and um, this gives us a additional check of our stiffness matrices. These additional checks are very important to know whether we are analyzing the structure correctly or not. So most of our, like when we are talking about multi-storied buildings, it is kind of different masses in series as we go on. So these kind of banded matrices give us that checking option, and also there are other parts which we'll not go into right now. These give us about tell us about the interaction between the different degrees of freedom also. Okay. So but I'm not sure about is there any specific other specific benefits, and maybe in civil engineering discussing about the benefits of matrices may not be a common practice, but in mathematics maybe it signifies a lot more in nature which we are not aware of, at least I am not aware of. Okay. So now, moving on to our assignment problem. So, our element 1 was this, and element 2 was this. We know that our L is equals to 6. We know lambda x. How much is lambda x and lambda y for this vertical element?
which is the starting and initial and final node. You got any
Yeah,
specific?
yeah, 1, 2, 3, 4. Like this is the A is starting and B is final node.
So lambda x is 0,
Yes, perfect,
lambda y is 1.
perfect. Yeah. So our transformation matrix looks like this. Please stop me if you find I am doing some mistake. Okay. And in the transformation matrix, what are the degrees of freedom? Pretty straightforward degrees of freedom. So now our stiffness matrix. So before finding the stiffness matrix, similar to what we did in the last class, like in the beam problem, we would find what are the value of AE by L. AE by L equals to 1. Then 12 EI by L cube equals to 1 again. Please check these answers. We already know AE and EI, right? You have noted down this,
Yeah,
right?
yeah, yeah, yeah.
6
Yes,
EI.
yes.
Okay. 6 EI by L square equals to 3. 4 EI by L equals to 12. And then 2 EI by L equals to 6. Okay, fine. Now our stiffness matrix K1. I will quickly write the stiffness matrix without consulting you, but I will take your help for the global stiffness matrix. Did we follow? Is it okay?
Yeah, yeah. It's clear. It's straightforward.
Yeah, straightforward. Okay. So now this stiffness matrix was in the local
Local.
level. Okay.
Yes.
So now let's take the global stiffness matrix. Global stiffness matrix would be transformation transpose into the local stiffness matrix into the transformation matrix. And this one I will directly write the answer. I could have given the student some time to solve it in class, but I don't need that, feel that is necessary. Mm, because we are only two of us here, so I'll just write down the answers.
Then you have to give me more time if you are expecting answer from me to.
No, no, no. Not because of that, but like if
It will
only
waste
you
of
are
time.
you are solving, then I am like I have enough trust on you that you can solve it. I don't want I don't want you to waste your time on this because you come up with very interesting questions. I like that part. Like you think about what is happening. So it is better we discuss about those things, and this is like just a matter of practice and attention, maybe concentration. Don't do things here and there. So this is the global stiffness matrix. Now for member 2. Member 2 is much easier, as you have already mentioned in the first part, that we don't require the transformation matrix in this case. 4, 5, 6. This is 7, 8, 9. So yeah, L is again equals to 6. Lambda x and lambda y, what would be that?
Lambda x is 1,
1,
lambda y is 0.
0, exactly. So your transformation matrix becomes
What
identical
happens
matrix.
if I change the initial node and the final node? Still, do we need to do the transformation? It is required, not required.
If we change the initial node and final node,
Hmm.
like this is from B to C. So if we are
Now,
taking it
if
from
I change to C to B,
C to B,
should we need to do the transformation, or still that element matrix and global matrix remains the same?
what do you think? What will happen?
It should change.
It should change, right? Yeah, it will change
So in that
because
case, we need to make it, do the transformation matrix, and we have to multiply and we have to get the global stiffness matrix.
yes, yes, yes. Like your lambda x will basically be -1 in this case.
Exactly. That is the question, because if if somebody has to change the initial node,
Hmm.
blindly we cannot say that okay, element and the global stiffness matrix will be the same there.
No, no, no.
So we
Hmm.
need to change the. I mean, provided if it is going from left to right, then I can assume element and global stiffness matrix is same. But other
Yeah.
way, if I change that initial node, then definitely I need to go back and do the. I mean, I'm just guessing.
Hmm.
I didn't try that,
No,
but
yeah. Yeah, that is correct. You are correct. Like if you change the initial node, you have to see that what happens, um, and it will change. It will not remain the same. Mm, Similar to a beam problem, if you are changing the initial node
still
for a
the
beam
T and T
problem.
transpose becomes identity matrix. I mean it.
Mm.
I mean I know I need to work on it to see that. If I
Uh,
change the initial and node, whether T and T transpose becomes again identity, again it
no,
remains
no,
same.
no. They don't become identity matrix. The
Yes.
reason is like you have, where is it gone? T transpose. Yes, yes. So now you have, it will not become identity matrix because now you have minus 1, minus 1, 1, minus 1, minus 1, 1 in the diagonal elements. Everything else will be 0. You only have a diagonal matrix, but minus 1, minus 1, 1, minus 1, minus 1, 1. Okay. Now we
Okay.
find that it is becoming identity matrix because everything is 1, 1, 1, 1, 1, 1.
Positive. Yes. Yes.
Yes. But that will not become identity matrix. That is clear. But what one can see again is that whether T transpose K and T becomes again similar to, like with what I mean is, if the minus 1 from this and minus 1 from that multiplies and again becomes the same thing, that we can that would be something interesting to find out.
Probably we have to work and we have to see that. I mean,
Yeah, we
I
have to
can't
work and we have to
do
see
I
that,
can't do
but
it in my mind, so I need to work and I have to do that.
yes, yes, yes. But I feel that there is a chance that it will come out to be the same matrix. The reason why I am saying so is, um, if there is a beam problem, so in beam problem we don't have the transformation matrix. Uh, we just start from this A. We just start from either A or B or B or A. We don't feel that it is left or right or right or left, right? So basically, this is a simple beam problem without any transformation matrix. Now,
But still, I can consider that 1, 2, 3 at the B and 4, 5, 6 at A, right? Still, in a
yes,
beam
yes, yes.
problem.
In beam problem, we can do that, right? So there is a chance, there is a high chance, and I feel that when you, even if you change the directions, you have the transformation matrix as minus 1, minus 1, 1, minus 1, minus 1, 1, diagonal matrix like this. So when you multiply this again with minus 1, minus 1, 1, minus 1, minus 1, 1, these minus 1 into minus 1 will actually give you the one man, because like what we are basically doing here is we are doing T transpose, then K, and then T. So when we multiply this and everything remains 1, the value of K doesn't change. It only becomes, the signs only change, right? If it is identity matrix, it remains
Got
exactly
it, got
same.
it. I think it will be same. It will be same. See,
Yeah, yeah. Hmm.
when we derive that element matrix, I mean, we consider that 1, 2, 3, 4, 5, 6.
Yes, but then
In
you have
case
to
if I
consider,
change
yeah, yeah, yeah.
the
Hmm.
if I change this B to 1, 2, 3
Hmm. Hmm.
and A as 4, 5, 6, then
Hmm.
I'll write that element as starting with 4, 5, 6, 1,
Four,
2,
five,
3, and
six,
4,
one, two,
5,
three.
6.
Yeah,
So
that you
that
have to
remains
do.
the same.
Yes,
That remains the same. That remains same. Okay.
yes, yes, yes. So that was that. Now, in this case, however, these are not necessary. This is out of context. In this case, we have the identity matrix, and so the identity matrix part is clear, right? How it has become identity matrix.
Yeah, yeah,
So
yes,
I am
yes,
not
yes.
writing the transpose part again. So I am just writing the I equals to K2, sorry, K2 equals to K2 global. I am not even writing the K2 global. Okay, equals to identity matrix transpose K2 identity matrix. Okay. and the value for this would be, I'll write that down, 1 0 0 minus 1 0 0 minus 3 0 1 minus 3 6 0 minus 3 12. Okay, this would be the different, yeah, these are the different values for the stiffness matrices for the members 1 and 2. So will you like to check once the stiffness matrix for member 2? Is it okay? The
I think that should be fine. I think that,
yeah, the different values are same as this one,
yeah,
because the length is already same as 6 meters. So okay,
I think
so
that should be fine. Yeah.
yeah, and more interestingly, one more part is like the length of the element is same, right? So if the length
Mhm.
of the element is same, the element stiffness matrix is the same as part 1 and part 2. There is only change in direction. Otherwise, the element stiffness matrix is same. A, E, and L, everything is same. Okay.
Provided
So
EI values are same. Yes.
yes, yes, yes. So the element stiffness matrices are basically the same, but in the first case, there is some transformation to that case. Okay. So these are the two element stiffness matrices. So now let's move on to the global stiffness matrix, the most important. This one I would like give you to solve it now, and then you can give me the answers, or we can solve it together also in class, no problem. Okay. So now whatever I was talking a little bit earlier, that we can just write down the two matrices and we can add the other parts. I will show you how we do that. So now what we have is in this,
First element we can directly copy the same values there up to 1 to 6 and
yeah, what I'll do, I'll just show you what I will do. What I'll do is I will write the stiffness matrix for element 1. Okay. So right now I am just copying the stiffness matrix of element 1. You just check whether I am copying it correctly. Okay. And I can also use different colored pens, so this would be easy to explain. Minus 1 0 3. Did I write the stiffness matrix of element 1 correctly?
yes.
Okay, this is correct, right? Okay, well and good. So now what we'll do is we'll write the stiffness matrix of element 2. But how we will write it? We'll write it like this. Say 1 0
Can write in a
0.
different color pen or with plus. Yeah, with plus. So
Yeah,
then it'll be
yeah, we
okay.
just do plus. Okay, 0 1 3, and then 0 -1 3, 0 3 12, 0 -3 6, and then the rest of the parts we can just write as it is. So what I feel is like, if it is this kind of continuous members in series banded matrices, so then the finding the assembled stiffness matrix is very easy, and most of the times we do mistakes in assembling the stiffness matrices, as I remember from my undergraduate classes. And we can just add zeros in which members there is no connection. So this is just, now this becomes 2, this becomes 0, this becomes 3, this becomes 0, this becomes 2, this becomes 3, this becomes 3, this becomes 3, this becomes 24. Okay, this is just simply the global stiffness matrix. We did not even have to check what was the degree of freedom associated to which column and what those things. Okay, so that was all. Then now comes the important part. Now we know the load vector equals to k global into displacement vector. The load vector is p1 p2 p3 p4 p5 p6 p7 p8 p9. With frames the only problem is like very long vectors, very long big matrices also. I'm just writing k global and I'm not okay, but I need to write it. I don't know how I will accommodate this. I'll just write k global and then I'll explain in that page. Okay, this is our matrix. Now what we need to do is, we need to first partition, like rearrange our matrices to get the that form, that k known unknown form, p known unknown, u known unknown. So our unknown degrees of freedom are 4, 5 and 6. Okay, so if we do p known, p unknown equals to k, that big one with partitions, equals to u unknown, u known. So in that case we need to bring u4, u5, u6 at the top, and p4, p5, p6 at the top. Okay, so from our last class what do we know? We know to bring p4, p5, p6 at the top, what do we have to do? Do you remember?
Yeah, first we have to take those three rows to the top without changing anything.
Without
P
changing
like
anything
that.
else, right? So what do? We just shift this up and we bring the other parts down. Like we interchange 4 with 1, 5 with 2, 6 with 3. Excuse me. Excuse me. Sorry. So we just interchange those rows and columns, right?
Yep.
Hmm. So let's do that. So big matrix, it is very difficult for me to write in this page.
But for P4, we are not changing the number, right? Load vector, it remains same as it is. Only when you are interchanging the column, we need to do that, right?
This is the load vector, right?
Yeah.
So we are changing the load vector, that is why we are doing this operation.
No, first we are interchanging the rows, right? Then we have to interchange the columns. When you are
Yeah,
interchanging the column,
we are interchanging the rows, then we'll interchange the columns. So what is the confusion? I didn't get it.
when you are interchanging the rows, that P1, P2, P3, that remains same as it is, right?
No. So if you interchange the rows, you are interchanging the rows to interchange the left hand side p values. So as we were discussing that day, that okay, I will just open that one.
No, 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 no,
If
no.
I have it here, say
When you are interchanging the rows, P remains same. Then when we are interchanging the column, that P goes up. When we are interchanging the columns.
no. Excuse me. So when we are interchanging the rows, we are interchanging the rows to interchange these equations. Like we have A, B, C, D, and we have this in matrix format. So if we want to do B, D, A, C, we interchange the row.
Okay. Mm-hmm.
You remember?
Yeah, okay. That equations, whatever that on the right hand side, that also it has to be changed. Otherwise, that no. Okay.
Yes. Just to interchange, just to make the difference in the left hand side, just to make the difference in the load vector, we do the row operation, and to make the difference in the displacement vector, we do the column operation. That was what we had understood last time. If we interchange the uh, displacement vector, we interchange the columns with the rows being intact. Okay. Do we remember that from last class?
Yeah, I remember
Okay.
that.
Hmm.
But somehow I was thinking that we will not be changing the load vector in the first row operations. Only when you change the column, we have to take it up. That comes. That's what
No.
I was thinking. Okay,
Then
fine.
like you are changing the then if you do that, then you are changing the stiffness matrix without any effect to the load and column, load and displacement vectors. But then you cannot change the stiffness matrix randomly, right? Then what is the need of assembling with so much
Agree,
care?
agreed, agreed,
Yes,
agreed.
yes. So now, with this, what is the new stiffness matrix? The new stiffness matrix would be okay. The new stiffness matrix would be like this: 1 0 3 2 0 3 minus 1 0 0 0 minus 1 0 0 2 3 0 minus 1 3 minus 3 0
Okay,
6.
got it. I understood. This U1, U2 remains same as it is. Only P we have to change. In the column operations, we have to take the U4, U5, U6 up. Okay.
Exactly,
Okay.
yes.
Okay. Fine.
0 minus 1 0 0. 0 0 0 Oh, okay, 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 okay. I did something else here. Why did I do that? I'm not sure. Maybe because the question in the previous year's question, it was like this. Yeah, just just check. The first, uh, this part is 0 here. The 0 block has come here and come here. Okay, but the 0 block here was something like this. So what did I do to the row operation? What I what have I actually done? Can you identify?
Go back to that
Yeah.
final matrix. I mean,
Yeah.
I've
L-
shifted that. Okay.
there is some difference in this in this load vector. Like, can you say what just by seeing this? Okay, I am also giving you this. This is P1, P2, P3. Can
This
you
should
say
be P7, P7, P8, 9, right?
yeah,
This
yeah,
should,
yeah, yeah. This is P7, P8, P9, and
then 4,
this
5,
is
6.
okay. I gave you the wrong one. This is 4, 5, 6. For that we are doing everything. Wait, P6. This is P1, P2, P3. So in P1, P2, P3, we assembled the first matrix, right? So the right hand
Hmm.
part was 0. This block was 0. So it has come
Exactly.
down here now. Yeah. And then this is 0 now in the next case. Okay. So this row operation part is okay. So now we have P known, P unknown partitioned. Okay. So then the next part is the column operation. Now what we have to do is we have to bring this U4, this U4, U5, U6 at the top, and we move the U1, U2, U3 at the bottom. So basically what we do here is, say, this part, we just pick this part up and we just drag it and place it here. Is it understood?
Mm,
We just pick
I
this
was
part.
thinking, I was thinking 789 will not change. It will be there as it is.
If 789 will not change, then this will not work. Like this one, what I am doing is, oh, okay, 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 okay. You are correct. You are
Because you have to interchange the column U4, U1 and U2
correct.
many
I
U6.
it is my
789 remains
yeah,
as it is.
yeah, yeah, yeah. It is my bad.
Probably 4, 5, 6 you have to
Yes,
move it.
yes, yes. It is my
4, 5,
bad.
6 you have to move it that side. Yeah, then it is fine.
Yes, yes, yes. Hmm. So this is what we are doing, and then this is actually, but also now we are also what we are doing is we are bringing this here like this, because we want like U1, U2, U3 at the end.
P7, P8 because you're keeping
Hmm.
P7, 8, 9, 1, 2, 3 like that.
Yes,
Okay,
yes,
clear.
yes, yes, yes. Yeah. Okay. So this is what we are doing. Okay. So if we do this, we will get hmm, P4, P5, P6, P7, P8, P9, P1, P2, P3. U4, U5, U6, U7, 8, U9, U3. Okay. And here, what is the answer that we have got? 203.
Banerjee, can we continue next week because another 15? I need to take another office call in another 10
Huh, huh,
minutes.
huh. Yeah, I will just complete writing this
Yeah, yeah.
matrix and then we can continue next week. Minus 1, 0, 0, 0, 3. I was planning to like just complete it here. 3, 3, 24. I am writing this matrix because like now you can also try this at home and check whether these values are matching, and if these are matching you can also solve the answer and keep it ready so that next class you can just verify whether my answers are correct. I know your answers will be correct, so you just check whether mine are correct. Zero minus 3, 12, 0, 0, 0, minus 1, 0, minus 3, 0, 0, 0, minus 1, 0, 3, 0, 6, 1, 0, minus 3. Okay, this is all, but now I'll just write 4, 5, 6, 7, 8, 9, 1, 2, 3, 4, 5, 6, 7. Okay, and for the last one, okay, I did not write anything here. So in this case actually it was 4, 5, 6, 7, 8, 9, 1, 2, 3, and here it was 1, 2, 3, 4, 5, 6, 7, 8, 9. The different degrees of freedom associated to this stiffness matrix. Is this understood?
Yeah, clear. Yeah.
Okay, so we'll end over here, and next class we'll just find out the answers, and I will
Okay.
upload this in the drive so you can check your answers with you.
Sure, sure, sure.
Okay, so that's
Okay.
all.
Thank
So
you.
yeah,
Thank you. Thank you.
thank
Bye.
you
Good
for
night.
joining us. Yeah, good night.